something impossible is happening again.
A few months ago, 3I Atlas, the third known interstellar visitor, entered our solar system at an astonishing velocity, an arrival that telescopes flagged as both rare and uncomfortably familiar. Initially, it glowed like an ember, muted, reddish, a relic of ancient dust. Scientists assumed they were witnessing a conventional cometary display. Then the color shifted to green, signaling diatomic carbon and cyanide emissions, signatures the community recognized and catalogued. But the change did not stop. In a development that has puzzled and frightened observers, the object shifted again, this time to an intense, bluer than solar emission. James Webb Space Telescope data confirm a chromatic inversion that defies standard thermal models. Wavelengths that should be scattered or absorbed are being emitted at intensities inconsistent with passive reflection. In short, 3I Atlas appears to be producing light. Comets do not do this. By every established thermal law, a small body approaching a star scatters short wavelengths, reddens, and emits mostly in the infrared. The surface temperatures remain many orders of magnitude below a photosphere. Yet, spectral analysis shows bands consistent with emissions at effective temperatures exceeding the photospheric baseline of our Sun. The paradox is not merely academic, it undermines assumptions about material behavior in stellar proximity and forces us to reconsider what constitutes a natural object. More unsettling is the temporal structure embedded within the emissions. Observatories across multiple continents have detected a faint but precise modulation, a pulse repeating every 247 seconds. The optical pulse corresponds with low-frequency radio hums and, in several cases, with transient infrared spikes. Multimodal resonance like this, coordinated optical, radio, and infrared signatures, suggests synchronized processes at the source. Harvard astrophysicist Avi Loeb characterized this event as a serious anomaly and proposed a cataloging framework. Under his model, 3I Atlas now sits among a set of observational inconsistencies that resist concatenation into a single natural explanation. The list is remarkable. An orbit unusually near the ecliptic, improbable angular approach, anomalous compositional markers including nickel-rich fractions, atypical of primordial small bodies, extreme dehydration compared with cometary norms, non-gravitational accelerations, and now the chromatic inversion. When probability estimates are combined, the resulting statistical weight pushes the scenario into the extreme tail, events that are unlikely to co-occur under random natural processes. Instrumentation from SOHO, STEREOA, JWST and ground-based coronagraph arrays recorded the chromatic transition during perihelion. The transition was not gradual. It occurred over a brief interval and was captured in synchronized time-stamped frames. Radiometers and spectrometers show that parts of the luminous envelope surrounding the body reached emission profiles that correspond to temperatures or energetic processes usually associated with hot plasmas, not with dirty ice and refractory dust. The luminous envelope extends outward tens to hundreds of thousands of kilometers, approaching scales comparable to planetary magnetospheres. Its morphology is structured, filamentary, and in several sequences geometrically ordered rather than purely stochastic. Scientists propose multiple hypotheses. One asynchronous idea is that electromagnetic induction between the solar magnetic field and an unusually conductive body could produce induced currents that momentarily heat localized regions. Another suggests exotic chemistry under unprecedented irradiation could transiently create short wavelength emission lines. These models struggle, however, to reproduce the repetition, coherence, and sustained nature of the observed emission. Some theorists explored engineered explanations, internal heat management, directed energy systems, or plasma drive exhausts that would manifest as blue spectral dominance. Such hypotheses verge on the extraordinary because they imply designed subsystems and functional architecture. Operationally, global observatories have coordinated an unprecedented campaign. Instruments from across the electromagnetic spectrum now collect continuous streams of telemetry. Radio arrays scan for structured transmissions. High-dispersion spectrographs seek narrowband features. Coronagraphs observe morphology. And magnetometers analyze perturbations in the local heliospheric field. The data pipeline is overloaded by terabytes of high-resolution frames, and open-source repositories are seeded with verified, time-aligned observations for cross-validation. The response is both scientific and geopolitical. Congressional or parliamentary oversight committees in several nations requested rapid declassification of imaging that agencies had previously restricted. Military and civilian sensor networks are interoperating with the scientific community to ensure global situational awareness. This is not panic, it is intense, methodical attention, because the object's characteristics touch questions of planetary safety, basic physics, and our place in the cosmos. As we approach the date when 3I Atlas will be nearest to Earth, which some projections mark in mid-December, the stakes increase. James Webb will execute pointed infrared spectroscopy. Hubble will produce finely sampled optical mosaics. Ground arrays will perform interferometry and polarization mapping. The objective is clear: determine whether the blue emission derives from internal energetic processes, external interaction with the solar environment, or some previously unknown natural chemistry. Conservative caution remains. The majority of the astrophysical community prefers models that expand known physics rather than leap to technological origin. New physics is a sober possibility and remains within scientific method. Hypotheses are formulated, predictions made, and experiments conducted. Yet the technological scenario cannot be dismissed outright, and because the implications are epochal, they must be rigorously tested. If the object harbors systems capable of temperature regulation, directed emissions, or propulsion that manifest as spectral blue dominance, then we would be witnessing an artifact of engineering, potentially ancient, autonomous, and self-sustaining. That outcome would answer some of humanity's most profound questions. Are we alone, and can intelligence persist across cosmological distances? The coming weeks will be decisive. Expectations range widely. Some models predict that the blue signature will fade as the body cools. Others forecast amplification as internal systems cycle, or as the object interacts with solar structures in unexpected ways. All models agree on one operational requirement: maximum data acquisition now. The community is mobilized for sustained observation. Amateur astronomers too play a role. Their distributed sensors augment the global network and provide redundancy. Ultimately, the mystery is not merely technical, it is existential. If a manufactured system traverses interstellar space and reaches our neighborhood, it would demonstrate that advanced agents can engineer durable artifacts across time and distance. If this is instead a sign of missing physical understanding, then our textbooks and our intuition about what matter does under stress require revision. Either way, 3I Atlas has forced a confrontation between curiosity and caution. We are witnessing a live scientific event that straddles the boundary between discovery and dread. Each photon that arrives from that distant blue glint is both data and a question. Watch, record, verify and remain skeptical, yet open. The universe has surprised us before. It may surprise us again.